Magnetic effect of electric current. In the previous standards, we have studied about magnets, magnetic lines of force, and magnetic field. It will be interesting to see that an electric current and magnetic field are related to each other. Come, let us now do an activity to study this relation. Activity. To perform this activity, we require a battery, a switch, a thick and straight copper wire, a magnetic compass, and some connecting wires. Let us first connect the circuit. Connect negative terminal of battery to one terminal of switch. Connect the other terminal of the switch with a wire. Similarly, let us connect another wire to the positive terminal of the battery. Mark the free ends of wires as A and B. Let us place the compass between these points. Now, connect the straight copper wire between points A and B in such a way that it is parallel to the compass needle resting in north-south direction. Close the switch and observe the direction of the needle. What do we notice? We see that the needle deflects towards the west. Let us now open the switch and interchange the connecting wires connected to the battery to reverse the direction of electric current. Let us now close the switch and observe the needle. What do we see this time? We observe that the needle deflects towards the east. This implies that when the direction of current flowing through a conductor is reversed, the direction of magnetic field produced due to it also changes. Thus, from this activity, we understand that the magnetic effect is observed because of the current in the wire. This means electricity and magnetism are related phenomena. But do you know who discovered that? Come, let us know about it. Introduction to Scientist. As a scientist at the forefront in the 19th century, Hans Christian Ørsted played an important role in understanding electromagnetism. He observed in 1820 that when a current passes through a metal wire, the magnetic needle near the wire turns through a certain angle. He pointed out the relation between electricity and magnetism. Today's advanced technology is developed as a consequence. In his honor, the unit of intensity of the magnetic field is termed as Ørsted. In the previous activity, we observed the magnetic effect produced in the conductor due to the electric current flowing through it. On the contrary, if a magnet is moved and kept moving, electric effect is observed. Isn't it exciting? Therefore, we are going to study magnetic fields and such electromagnetic effects. Come, let us first study the concept of magnetic field produced around the conductor by performing an activity. Activity. Let us first take a rectangular cardboard. Pass a thick copper wire through its center. Now, we shall connect a 9 volts battery, an ammeter, a plug key, and a rheostat in series with the wire. Now insert the plug key. Let us adjust the rheostat so that 1 ampere current flows through the copper wire passing through the cardboard. Bring a compass needle close to the wire. What do we observe? We observe deflection of the needle as the compass is moved towards the wire. Mark the direction of the deflection shown by the needle with a pencil. Let us now keep the magnetic needle at some other position on the cardboard. Observe the direction of the deflection shown by the needle. Mark this direction as well. By keeping the magnetic compass at different positions on the cardboard, note down the directions of the deflection at each of these positions. The direction of the current shown in the circuit is its conventional direction. Let us now keep the magnetic needle on the first position. Increase the current flowing through the copper wire by adjusting the rheostat. Do we see any difference in the deflection of the magnetic needle? Yes! The extent of deflection in the needle is more than that in the case when the current flowing through the circuit was 1 ampere. This means that if the current in the wire is increased, the extent of deflection of compass needle from the resting position is more, indicating greater strength of the magnetic field. Let us now decrease the current flowing through the copper wire by adjusting the rheostat. What do we observe? This time the needle gets slightly deflected from its resting position. This indicates that if the current in the wire is decreased, the compass needle shows slight deflection, indicating low strength of the magnetic field. Let us now adjust the current through the copper wire to 1 ampere. We can see a deflection in the compass. Now take the compass little away from the wire. What do we observe? As the compass is taken away from the wire, the compass needle starts coming back to north-south direction. Let us now sprinkle iron filings uniformly on the cardboard and tap the cardboard gently. What do we observe? The iron filings arrange themselves in circular manner of varying radius around the wire. This is because the magnetic field lines of straight current-carrying conductor are circular in nature. Thus, the iron filings spread along the magnetic lines of force. Always remember, a magnetic field is produced along a straight current-carrying conductor. If the current is unchanged, the intensity of magnetic field reduces as the distance from the wire increases. Therefore, the concentric circles representing the magnetic lines of force are shown bigger and rarefied as the distance from the wire increases. If the current through the wire is increased, the intensity of the magnetic field increases. Right-hand thumb rule. If the direction of current is known, then the direction of the magnetic field is given by the right-hand thumb rule. This is a convenient rule for finding out the direction of the magnetic field produced by a current flowing through an electrical conductor. According to the right-hand thumb rule, imagine you have held a current-carrying conductor in your right hand in such a way that the thumb points towards the direction of the current. Then the curled fingers around the conductor will give the direction of the magnetic field lines. The right-hand thumb rule is called Maxwell's corkscrew rule. Do you know what is this corkscrew rule? According to Maxwell's corkscrew rule, imagine driving a corkscrew in the direction of current. Then the direction in which we turn its handle is the direction of magnetic field lines. Come, let us now study the magnetic field pattern produced around a circular loop. Magnetic field due to current through a circular loop. We have learnt about the magnetic lines of force of a magnetic field produced by a current flowing through a straight conductor. But do you know what will happen to the magnetic lines of force of the field produced by a current flowing through a loop made by bending the straight wire? Come, let us find out. Here, one setup is shown. A circular loop of a wire is connected in this setup. Iron filings are sprinkled around the loop and the current is allowed to pass through the loop. On tapping the cardboard, we see the magnetic lines of force are produced at each point on the loop. The magnetic field lines are circular near the current-carrying loop. As we move away, the concentric circles representing magnetic field lines become bigger and bigger. At the center of the circular loop, the circle of magnetic lines of force becomes so big that its arc can be shown as a straight line. Here, the magnetic lines of force are shown near the points P and Q only. However, they will be created near each point on the loop. Likewise, each point will produce magnetic field at the center of the loop. By making use of the right-hand thumb rule, we can check that every point on the loop contributes the magnetic lines of force at the center of the loop, and these lines of force at the center of the loop are in the same direction. We have seen in the experiment that the intensity of magnetic field at any point produced by a current flowing through a wire is dependent on the current. This means that if there are n turns in the loop, the magnetic field produced would be n times larger than that produced by a single loop. Come, let us now study the magnetic field pattern produced around a solenoid. Magnetic field due to a current in a solenoid. When a copper wire with a resistive coating is wound in a chain of loops like a spring, it is called solenoid. Whenever an electric current passes through a solenoid, magnetic lines of force are produced. The solenoid can be considered as circular coils placed side by side. One end of the current-carrying solenoid acts as a south pole and its other end acts as a north pole. Outside the solenoid, the magnetic field lines travel from north pole to the south pole. The end of the solenoid having clockwise circulation of current in the transverse view forms the south pole, while the other end, where current can be viewed to be flowing counterclockwise, forms the north pole. We are aware of the magnetic lines of force of a bar magnet. The properties of the magnetic field of a solenoid are very similar to the magnetic field produced by a bar magnet. The magnetic lines of force inside the solenoid are parallel to each other. Can you tell what does this mean? This means that the intensity of magnetic field within the solenoid is uniform everywhere. This indicates that the magnetic field in a solenoid is uniform. Till now we have studied the magnetic field pattern due to the current passing through conductors of different shapes. Let us now understand what happens when a conductor carrying current is placed in a magnetic field. Force acting on current carrying conductor in a magnetic field. Let us perform an activity to understand this concept. The apparatus required to perform this activity are a thin flexible copper wire, 2 electric cells, a horseshoe magnet having a strong magnetic field, a plug key, connecting wires and a stand. Let us now connect the circuit. First, we shall fix the thin flexible copper wire using a stand. Now connect the upper end of the wire to the battery. Connect the lower end of the copper wire to one end of the plug key. Then we shall connect the battery to the other end of the plug key. Always remember to keep the key open while making connections between apparatus. First, we shall take a horseshoe magnet. Let us hold it in such a way that the copper wire is between the poles of the horseshoe magnet. What do we observe? We do not see any movement in the copper wire. This indicates that whenever a current is not flowing through the wire, it remains straight. Let us mark this position of wire as A. Now, close the key and allow the current to flow in the circuit. Let us observe the copper wire. Do we see any movement in the wire? Yes. When the current flows from top end of the wire to its bottom end, the wire bends. Let us mark this position of wire as C. Let us now keep the plug key open. We observe that the copper wire becomes straight again. That is, it again comes back to position A. Now change the direction of current flowing through the wire by reversing the connections. That means now the current is flowing from the bottom end of the copper wire to the top end of the copper wire. Close the key. What change do we observe in the position of the wire? This time also the wire bends, but it deflects to the opposite side of the position C. Let us mark this position of wire as B. Bending of copper wire when placed in the magnetic field is possible only when the force is exerted on it. Thus, from this activity we can conclude that whenever current flows through a conductor in the presence of magnetic field, a force is exerted on the conductor. If we take the directions of magnetic field, direction of electric current, and that of the force on the wire, then we come to know that the direction of the force on the wire is perpendicular to both the magnetic field and the direction of the current. In the previous activity, we have seen that when the direction of the current is reversed, the direction of the force also gets reversed. This means that the direction of the force depends on both the direction of the current and the direction of the magnetic field. Now can you tell what will happen if the magnet is kept reversed? That is, what will happen when the direction of the magnetic field is reversed? When the current flows from top end of the wire to its bottom end, and if the direction of the magnetic field is reversed by reversing the poles of the magnet, then the wire bends to the position B. That means, even after interchanging the poles of the magnet, the direction of the force of copper wire is reversed. Let us now answer one more question related to this concept. Experimentally, it is possible to show that the force on the conductor is maximum when the direction of the current is perpendicular to the direction of the magnetic field. How can we do this? Come, let us understand. First, we shall arrange the apparatus as shown here. Let us keep the wire in between the two bar magnets as shown here. That means the magnetic field is perpendicular to the position of the wire. Now, allow the current to pass through the wire. We can see that the wire gets lifted upwards. Now let us keep the wire at an angle to the magnetic field. What do we observe? We see that the wire gets lifted upwards this time also. But the extent to which it gets lifted is less as compared to that in the case when it is kept perpendicular to the magnetic field. Now let us keep the wire parallel to the magnetic field. Do you see any change in the position of the wire? No. The wire does not deflect from its position. That means no force acts on a current-carrying conductor when it is parallel to the magnetic field. This showed that the deflection of the conductor is maximum when the conductor is kept perpendicular to the magnetic field. If the direction of the current in a conductor and the direction of magnetic field are known, then the direction of force acting on the current-carrying conductor can be found out by using Fleming's left-hand rule. Come, let us study this rule. Fleming's left-hand rule. When a current-carrying conductor is placed in a magnetic field, a force is exerted on the conductor. There is a simple rule to determine the direction of force acting on a current-carrying conductor placed in a magnetic field. This rule is called Fleming's left-hand rule. According to this rule, the left-hand thumb, index finger, and the middle finger are stretched so as to be perpendicular to each other. If the index finger is in the direction of the magnetic field and the middle finger points in the direction of the current, then the direction of the thumb is the direction of the force on the conductor. Come, let us now verify this rule by performing an activity. Activity. Consider the same setup shown in the earlier activity. Let us now determine the direction of force on the wire using Fleming's left-hand rule. Here, we are using vertical current-carrying conductor placed in a magnetic field. The direction of magnetic field is from north to south. The direction of current is vertically downwards. We can see the conductor getting deflected towards the position C. Now let us verify the direction of force by using Fleming's left-hand rule. Let us stretch our left hand so that the forefinger, center finger, and the thumb are perpendicular to one another. Now the forefinger is pointing from north to south, that is in the direction of the magnetic field. The center finger is pointing downwards, that is in the direction of an electric current. Now look at the direction of our thumb. The thumb is pointing towards the position C. This gives the direction of force acting on the wire. Similarly, we can verify the direction of force on the wire kept in magnetic field when the current is flowing in the upward direction through the wire. In this way, the direction of force acting on the conductor can be verified using Fleming's left-hand rule. Come, let us now proceed further.